Okay, then, welcome to the second lecture of algorithmic meta-theorems. Today, we will be talking about Treewidth and perhaps also cover a Coself theorem already a little bit. At first, some announcements. So next week, there will be no lecture as it's the national holidays. And for the exercise sessions, we will have an online session and an offline session. The online session will be Fridays at 9:15, and the offline session at 11. And you can sort of choose yourself which session you want to attend. And the first session will be on the 19th. So still, I think, 1.5 weeks or so to go. Yeah, that's about the organizational matters. Any questions about that? If not, then after the rough overview that we got last time, now we're going to start getting a little bit more into details, taking it a bit slower. So we're going to start with trees and Treewidth. We already saw that you can solve a lot of stuff on trees via dynamic programming, and we want to now generalize this approach to the concept of Treewidth. We're going to introduce it and cover it slowly, and yeah, then afterwards we're going to cover Coself theorem, which states that a lot of problems can be solved in graphs with bounded Treewidth. So last week we saw this very simple algorithm to compute a maximal independent set on a tree, which kind of worked by keeping these dynamic programming tables and traversing for the leaves and then pushing the information up and up until you reach the root, and then reading the information from the root. Let's now formalize this a little bit. So if we have a vertex u, then let's say Tu is the subtree at vertex u. So the subtree where u is the root. And then we want to compute for every vertex in the tree 2 values. So for vertex u, we're going to compute mu with the value 1, which should be the maximal independent set in the tree Tu that includes u. And we're going to have another one, mu0, for the maximal independent set that excludes the value u. So if this is the tree Tu, where u is the root here, then we only compute 2 values. And so in a sense, we want to compute the maximal for all ways that a vertex can intersect the vertex u. We want to compute the maximal bound solution. And why is this sufficient? Okay. So you can think of, we want to push the information upwards. So if we have this subtree here at the vertex v1, then this subtree can contain an independent set somewhere. But this vertex v1 is going to be a separator to the remaining vertices of the graph. So if we have an independent set here outside in the rest of the graph, there are no edges that go anywhere towards the subtree. The only place where an edge can go is towards this vertex v1. This is the crucial part. So if we have any kind of solution in the subtree of v1, we don't need to worry about anything except whether this separator vertex v1 is included or not. That's the only way to distinguish 2 solutions from the outside. So for those 2 ways that you can distinguish a solution, we're just going to keep the best of both. And this will be our mu1 and mu0 that we defined up here. And how do you compute this information inductively? So this is given by the following recurrence equations. So let's say we want to compute mu1. This is the maximal size of an independent set that includes the vertex u. Then we know already that it includes the vertex u. This means it cannot include any of its children. But inside the subtrees, we don't have any further restrictions, since there's no edges like this. There's no edges that prevent us from adding any vertex inside the subtrees except for the direct children of u. So we can just take in each of the subtrees, we take the best solution we can get that excludes u. And this is going to be this term. We get a +1 for the vertex u that we add to the independent set, plus we sum over all children and take the maximum independent set that excludes the child. This is clear so far? Great. Similarly, we proceed with mu0. This is the maximal independent set that excludes u, so we don't get this +1. But in the children, we have all choices. We have no restrictions whatsoever, so we can take the maximum of the independent sets that includes u or excludes u, which is just the largest independent set in each of the subtrees. So far, this should perhaps be already familiar from bachelor lectures, and we try to generalize this now a little bit. So we don't only want to work with trees, but also with tree-like graphs. So here, this graph on the right kind of looks like a tree. And the reason that the previous algorithm worked is because every vertex was a separator. So if you had such a subtree here, then you had a single vertex that separated the subtree from the rest of the graph, and you could just store all ways that an independent set could intersect its solution. And now in this graph, we have these separators which are a little bigger. They contain now 2 vertices. And we're just going to store all ways that a solution can intersect these 2 vertices. So we're just going to keep the same idea and generalize it to larger separators. So let's try to do this here on the picture. We consider the subtree here defined by the boundary of the vertex x and y. So x and y act as a boundary, and then we have this subtree below. And we can store the same kind of dynamic programming table. So we have these vertices x and y, and we can enumerate all ways in which an independent set contains these vertices. Either none of them are included, or only y is included, only x is included, or both of them are included. And then we can store, then we can store the maximum independent set for these ways that the vertices are included or not included. So we can assume, for example, that in the subtree of x and y, the largest independent set that excludes x and y has size 5, the largest one that includes only y has size 6, and we notice the largest independent set that includes both x and y has size -infinity because it doesn't exist. So non-existent values, we can encode them by -infinity. And why is it? Because if you contain x and y both, there's an edge between the two, and you don't have an independent set. So now we want to push the information upwards, but unlike before, where we grouped information of the children and put them into the root, we're going to do it in a 2-step process. So next, we would like to consider only this subgraph of u and v. So we can make a similar table for u and v, and then we can have 0, 0, 0, 1, 1, 0, 1, 1. So who can say what the largest independent set is in this subtree that contains neither u nor v? Anybody? Yep.
We'll be keeping y, 6. Yes.
Yeah, I guess we would keep this value here. And why is that the case?
It's the maximum overall entries on the lower level.
Yeah, it's like if we don't choose u or v, we have absolute freedom in the subtree below, and we can just use the maximum entry that there is. And you're right, that would be 6. What happens if we want v to be included, like this? That's the next row. Yeah.
And we have take 0, 0, so neither x nor y.
So we would have to look here.
Yeah.
And why is that the case?
Because x and y are both incident to v.
Yeah, if we enforce v to be in the solution, then x and y cannot be in there. So we have to take a look there. So we get a value of 5 in the subtree, plus 1 for the vertex V itself, so we get a 6 here. Similarly, we can proceed if only U is in the solution, then what do we get? If U is in the solution and V not, then we cannot take X, but we may take Y because there's no edge between U and Y. So that would be 7, I guess, because if we include Y, we are here at the 6 value, plus 1 for the U, so we get 7. And yeah, minus infinity if we put both values in. And now the picture kind of looks like this. We can forget about X and Y, and we only need to see U and V and the subtree that is connected to it. We can do the same thing for the other side. We have a table here, and we push the information upwards. And then we have these two new tables. They're with respect to the same separator, but for one for the left side and one for the right side. Next, we would like to merge these tables to get a solution for the whole subtree of U and V. So how would that look like? So if neither U nor V is contained in the solution, then what would be the solution size? Does anybody have an idea? Yeah. 8. I would say 14, because we know that if neither are contained, here we get an 8 on the right side, and here we get a 6 on the left side, and we add them up, and we get a 14. Okay, things get a little bit more tricky if we are in the situation where V is included. Then what do we get on the left side? Here we get a 6 as well. And here we get a 3. So do we get a 9 in total? Exactly, we only get an 8 because the 6 on the left side includes the vertex V, and the 3 on the right side also includes the vertex V. So we're counting V twice. So we have to subtract it once. So we only get 8. Similarly, we can proceed for the other table. Here we have 7 here, and 9 here would be 16, minus 1 would be 15. And we get a nice table like this. And now again, we can forget that we originally had 2 different subtrees. We could just merge them like this. And if this is the whole tree, then we're kind of done. We can look for the maximum value at the end table, and we see the maximal solution would be 15. So the difference to the previous approach is now that we have 2 phases. Before we merged all children together, and now we just merge one child at a time, and afterwards group them together. And that we have larger separator, but the principle still stays the same, I would say. So really the concept that we used is that we had these small separators that only had size 2 in our case, and that partitioned the whole tree, that you could traverse up these separators. And now comes the magical part. I want to formalize this, and it's not immediately obvious how you get some nice property that exactly has these separator properties that we want, but the notion of tree width does exactly that. So we're going to define so-called tree decomposition, which will be a sequence of separators that are ordered in a tree-like fashion. That will just be like the separators in the previous tree that we considered, and that we can later on traverse upwards in a dynamic programming fashion. And let's see what this separator tree needs to, what properties it needs to have. So the first property that we need, that every vertex of the graph will be contained in some bag. So the bags will be sets of vertices of the graph. Like here, this bag here contains vertices A, B, C, and here for another bag that contains another 3 vertices. And the first requirement would be that every vertex occurs in some bag somewhere. these are going to be three properties that we define, and then we say the tree on the right will be a tree decomposition of the left graph. The next property we need is, if there's any questions right now, feel free, just shout in. This is going to be a very important concept for the rest of the lecture and for the next lecture as well. So it's really important that you completely get this. Okay, second property is that every edge should be contained somewhere in the back. So if we have an edge between B and G, for example, we will require that some back in the tree contains both the vertex B and the vertex G. That also sounds pretty natural, I would say. The strangest requirement is the third one, which is that for every vertex V of the graph, the back induced by V, so if you take all the backs that contain V, that they should induce a connected subtree. So this sounds a little bit strange. What does it really mean? Let's say we take this vertex G on the left, and then we mark all the backs that contain G using this purple color, which would be these three backs. We require that these three backs together are connected in the tree. So we would say it should be impossible that G is in this back, for example, because then there is a back that does not contain G in between, and the G backs would not induce a tree. So this sounds a little bit strange at first, but we will soon see why this is actually a very nice property. And if such a tree decomposition satisfies all these three properties, we say it is a tree decomposition, and we can define the width of it. And we say the width of the decomposition is the size of the maximal back minus 1. So here, in this example, the tree decomposition has a width of 2, because every back is size 3. And for technical reasons that we will see soon, we subtract 1 from the maximal number, and then we get the width. And if we have the width, we can define the tree width of a graph, which is simply the minimum width among all possible such decompositions of the graph. So we take the best tree decomposition that we can find, look at the largest back, subtract 1, and that's going to be our tree width. And now let's talk a little bit about this third strange property here, that all the backs induce a subgraph, a subtree. And let's consider it why we need that. So what we will see that we get these separated properties that we talked about earlier. So we mark here this back, for example, BEG, and we will see that it has some nice separated properties because of the third bullet point. And the separated properties that we get are the following. Let's remove all the vertices that are not in BEG. So here we remove B and G, G and E is left here. So we see now that BEG acts as some kind of separator on this graph. So here on the left subtree, if we ignore the vertices in the back, we only get F, and here we only get H, and here we only get A, C, and D. And in the graph, if you want to traverse from, let's say, the vertex F to to some vertex A, like this, you will have to go through the back. This is the nice property that we get from the third bullet points. And why do we get that? Let's say we could traverse from A to F without going through the back. Then we know that there is an edge AF, like this. And because of the third bullet point, hang on, this edge AF needs to occur somewhere together in the tree. and then one of the vertices A or F would also be inside the bag. Okay. First nice observation would be that trees have Treewidth 1. Maybe everybody take a moment, try to come up with the decomposition of a tree that witnesses that trees have Treewidth 1. How would one go ahead and proving such thing? Maybe everybody take a moment to think about it if they haven't already. So we want some kind of decomposition that satisfies all these properties, and every bag should contain only 2 vertices. This is a tree, then how could you construct tree decomposition with one of this? Yeah.
For the edge, we introduce the back, and then we just can connect the backs according to the graph. So we have the back BE and the back CE and the back BA. And if they have one common vertex, then we just connect the backs.
Oh, that's right. So we create a bag for every edge, and then we connect them according to the shared vertices. So it would be like this. If we had another vertex X on top, we get another bag PX like this. So you're right, we create one bag for every edge, and then if 2 bags share a vertex, we connect them in the tree. Or at least we connect them to the successor. Yeah.
Yeah, there's one we connect all the bags that have at least one vertex in common. We have triangle.
Yeah, this does not sound right. That's true. So just connect it to the upwards successor. So this is now why we defined the tree width to be the width -1, because then trees nicely have tree width 1. Otherwise, it would be a bit ugly. That's the only technical reason why we do that. Any questions about tree width so far? Okay. If not, then we would start with our first theorem, which is actually wrong. Should be. Okay, let's read it. So if we assume we have a graph G and we're given a tree decomposition of the graph of width W, then one compute the size of maximum independent set in time 2 to the W times some polynomial in W times n. So for every fixed W, you get a linear time algorithm that computes the largest independent set. So this is a very nice result, and it can be obtained exactly using the techniques that we witnessed already. And this will be the first example of a problem that you can solve on a graph where the tree width is bounded by a constant, and there will be many more such algorithms that we see. And yeah.
Do we need this omega to the power of O1 that contained into the omega?
So it's a W for the width.
Oh, W.
I'm not 100% sure if it can be pushed into the exponent, the O there.
It's forward to the W, and then you just have a constant 2 times to the W. Oh, I see what you mean. Sorry, yeah.
So for sure you could write it like this, if you just put an O to the W in the exponent, but sometimes it's nice to get the exact exponent of the for the W, and then I think you have to consider the polynomial factor as well. Okay, so How, or any other questions so far? Then let's talk about how we get this result. So we have this tree decomposition given, and the first thing we're gonna do is we're gonna root this decomposition. So we're gonna pick an arbitrary vertex of the decomposition and declare this is gonna be the root now. In this example, we chose ABC to be the root. And now we need some definitions for the rest of the lecture. These definitions will come up over the next slides, so let's remember them carefully. So we have a bag I, so I usually now index the bags by I, J, K and stuff like that. And then we have BI to be the vertices that occur within the bag. So in this example, if we have the bag I here on the right, then BI would be the 3 vertices here. Similarly, we're going to also define VI, which will be all the vertices that are contained in the bag itself, together with all the successor bags, all the children bags. So in this graph, we have these 3 children of bag I, and we take all the vertices in these 3 bags, and this is going to be our VI. So far, so good. And we're going to again do the same principle of computing the solutions in the subtree with respect to the boundary. For trees, the boundary contained only single vertices. In the second example, the boundary contained 2 vertices. And now the boundary will be exactly these bag vertices BI. And the subtree in which we compute the solution will be the set VI. So what does it mean to compute solutions with respect to boundary inside a subtree? We're gonna formalize it soon. But I said here that the vertices BI will be a separator. So let's prove this perhaps. So the statement I want to show is that for every bag I, the vertices in BI inside the bag will be a separator between VI, this is going to be the children below, and V minus VI, which will be the vertices above in the tree. And what does it mean to be a separator? It means that if you want to traverse from VI to the complement of VI, you have to go through at least one vertex in the bag. So here as an example, we see if you want to go from F to A, you would have to go through B, which is inside the bag. So in other words, if you take one of these vertices which are not inside the bag, then there's no edges to vertices that lie above. That's a statement we want to prove. And for contradiction, let's assume that the statement is not false, and we have some counterexample graph like this one, where we have this edge that goes between the 2 sets and both endpoints are not contained in BI. And by the properties of the tree decomposition, we know that this edge A and F, it needs to occur somewhere in the tree decomposition. We don't know where exactly, but let's just assume for now that it occurs somewhere here in this bag AF that lays above the bag BI. Then also we see that this vertex F here, it lays in the bag below our bag I. And we know that all the bags that contain F must induce a connected tree. What does it mean? This bag contains F, this bag contains F, and all the bags in between also must contain F, and that's our contradiction. And you could get the same kind of contradiction if you assume that this edge AF doesn't lie above, but maybe lies here, AF. In this example, then you would notice, okay, here is A, here is A, and also here is A, another contradiction. Yeah, that's the statement we just had. And that's the proof about the separator theorem. So in fact, the situation looks like this, that we have a subtree and a bag that acts as a boundary to the remainder of the graph. So what are going to be the solutions that we're going to store? All the ways that a solution can intersect the boundary. And we formalize this as follows. For every subset of vertices of the bag, we define, of a bag Mi, we define Mi of S. And it is the maximum size of an independent set in the subgraph induced by the subvertices of the I that intersects the boundary exactly in S. Here's an example in the picture below. We have our bag Bi, it's going to be these gray vertices, and our set S will be the vertex, the set that contains only B. Who can tell me what Mi of the set that only contains B is? So it is the size of the maximal independent set in this subgraph that contains this vertex. That's the requirement. And it should not contain this vertex, and it shouldn't contain this vertex. So it should intersect the boundary exactly in B. And then the only way, or the maximal solution that we can get, is we cannot include this vertex because it has an edge to B, and B should be contained. On the other hand, H still can be included because there's no edge anywhere. And yeah, you can easily see that the best you can do is these two vertices. So Mi of just B will be 2. On the other hand, what is Mi of the set BEG? Will be the maximal independent set that contains both B and E and G.
Minus infinity.
Yeah, exactly. It's minus infinity because there is no such set. And the thing that we will refer to as table entries will be this function MIS. So for every such S, we store a table entry, and this will be Mi of S. And just as before, we will compute these entries all the way up to the root. And before we do that, we're going to modify our tree decomposition a little bit to get some extra nicer properties. So here on the right, we have the tree decomposition we saw already. And on the left, we have what we call a nice tree decomposition. And why is this tree decomposition nice? Because it has some extra properties. And for example, we have so-called forget nodes, which are those nodes which contain exactly one less than the children. So here this bag contains A, B, E, and the bag above does not contain E, and it has exactly one child, and we call it a forget node. Important, one child less, one vertex less, and exactly one child, that's a forget node. And we're going to break down the nice tree decomposition in these simple nodes, and then we're going to discuss how to process them separately. Yeah?
Those are generated from different original graphs, right?
They both represent the same graph, yes. Okay. And soon I'm just going to sketch how to convert the one on the right to the one on the left. But first, let's discuss what the properties are on the left. And the first one is that we have so-called forget nodes, which are those that have one sub bag and exactly one vertex less than that one. The complement of this would be an introduce node. It works the other way around. They also have one bag below, but they have one vertex more than the bag. So they add one vertex to the bag. Third kind of thing would be join nodes. Here, join nodes are the only nodes in the nice tree decomposition that have two children, but these two children should be identical bags. So we see the join node itself contains B, C, E. then also the two children should be BCE and BCE. Yeah.
There's a typo there in that line one, it should be a BE and not a BC.
Where?
Just above the join node.
Above the join node, that should be a BE, you say?
Yeah, because
That sounds,
the subtree for E is
that sounds right, I guess. Oh, no, no, what did you say should be there? B.
because then it's an introduce node because it introduces A.
Or the introduce node could also be ABC, I guess.
But at least I know that there should be an E there because otherwise the E subtree is disconnected.
Yeah, that's a good point. Yeah, I got that wrong. Yeah. Otherwise, the subtree would be disconnected, as you said. Then, so I guess it should be BE. Yeah. If you find any slide notes mistakes, tell me, so then I can fix them for the next iteration. Okay. Yeah. Join nodes, two children, and they contain exactly the same vertex in the back. The next one would be leaf nodes, which should just be empty bags. So that's also allowed, that the bag is empty. And the last property is that we have a root node that also is an empty bag. So yeah, for reference later, it's also written there. And now how would you translate the one on the right to the one on the left? You kind of look at the, let's say, you squeeze in some bags in between that. So here in between, if you want to go from BCE to ABC, you can find a sequence of first removing all the vertices that are only in BCE. Which one would that be? I guess you have to remove the E, and you're left with BC. And then next, you can add the A, and you're there already. If the intersection is smaller, you have to make some steps in between, but yeah, it's possible, I suppose. And then to get the empty root, you just remove one vertex by one. So you have lids AB, you remove that one, and then you have only A, and then you have the empty set on top.
So
Yeah, you can read that.
suppose the typo was in the ABE bag, that should be an ABC.
This should be an ABC. Yeah, maybe that's a typo. Yeah, thanks. Any questions about nice tree decompositions so far? And they're nice because soon we're going to do the dynamic programming. Then you only have to consider the cases where you only add a vertex, remove a vertex, and do this nice join operation. Yeah, one question?
Should it be binary or is that not important actually?
It should be binary, yes. So you can make, if you have a larger branching, you can make it binary by always branching one thing more in. So let's talk about how we do the dynamic programming. Once again, to remember, the set Mi of S will be the maximum independent set in the graph induced by the subvertices Vi that intersect the bag exactly in the set S. And this is going to be this table entries. For every bag I, we store this value where we iterate over all subsets S. And we note that there are 2 to the size of Bi many such subsets. So each bag has size W only, so there's 2 to the W subsets. So we only need to store for every bag 2 to the W many entries. And this is the 2 to the W of the running type that we saw earlier. And we're going to define a recurrence relation if you have the values for the children that difference the parent values in terms of the children values. And I guess we're not going to start with the leaves. So we have a leaf bag I, and here we have it here. And because the tree decomposition is nice, we know that the bag is empty because it's a leaf. So the bag itself is empty, and since it has no children, Also, the induced subgraph of VI is empty, and this makes it very easy to compute the solution. You can tell it. What is MI I of S? First of all, what are the possible values of S? Just the empty set. Yeah, maybe it's too easy. So we iterate over all subsets S of the empty set, and there is just the empty set as a subset of the empty set. So we only need to compute MI of empty set. And so it is the maximal independent set in the graph G induced on the empty set. And yeah, of course, it's then 0. Because there can be no vertices in there. Graph is empty. Much more interestingly, though, is the join operation. And here we have this back BCE with 2 children that are again BCE and BCE. The join back is back I, which has children J and K. And because the decomposition is nice, we know that BI and BJ and BK will be the same vertices. That was the property of nice tree decomposition. And from this, we can conclude some facts. It implies that the vertex set VI, so all the subvertices of back I, will be the union of Vj and Vk. And additionally, that if you intersect Vi and Vj, sorry, this should be Vk and Vj, you get exactly the vertices in the back. So the picture kind of looks like this one below. We know the solution in Vj, we know the solution in Vk, and we know that Bi is the boundary between these sets, and we want to have a solution for the union of the 2 sets. And we can do the same trick that we saw earlier. Let's say we want to have a solution that intersects the boundary exactly at these 3 vertices. These 3 vertices will be our set S. Then we know on the left-hand side, there's a value mj of S. So maybe here we have 7 vertices, for example. And on the right-hand side, we know the value mk of S. So maybe here we have 8 vertices on the right side. Then we can just add them together. But we have counted the 3 vertices in the middle twice. So we have to subtract them again, which means to compute the value in the union, we add the one solution on the left, solution on the right, subtract what we counted double, and that will be our solution for the union of the 2. Okay, so far so good. Next one would be the introduce operation. Here we have back the example BCE, which introduces the vertex C to its child back. So here it contains exactly the vertex C additionally. And what are we going to do? The picture kind of looks like this. We have the subtree Vj, goes like this. That's the child here. But then we have this additional vertex C, for which we don't know anything yet. And again, we distinguish 2 cases. So let's at first assume that C is not in S. So we want to find the largest independent set in the subtree Vj, which does not contain C. But then we can just look at the solution already. Because here, this subtree does not contain C, and we know everything about the subtree. It gets a bit more tricky if we want C to be inside the solution. But then we can take a look. Within the set S, let's say here in this example, we enforce that these 3 yellow vertices should be inside the set. And let's say there is an edge like this between the 2 of them. Then we know that the solution is -infinity, because there can be no independent set where two vertices are adjacent. On the other hand, let's assume that there is no such edge. Then things start to look a little bit better. We also know that there is no such edge here. And we can just take the largest independent set in this subtree and add a +1 for the vertex C. And this is going to be the solution. So we remove C from the set, look into an existing table, and if it is an independent set, we add +1. And if it's not an independent set, then it will be 0 or minus infinity. I guess minus infinity. Any questions in between, just shout in. The forget operation is going to work similarly. Here we are forgetting a vertex G. Ah, yeah, here. So this vertex G is forget from the table. And the picture looks like this. In our new bag, BI does not contain G. So here we have BI and G lies outside. But we have a solution already for the instance where G is contained. There we know everything. And the set VI and VJ, they are identical because it's a forget node. And then we can just look in the entry in the table and see what about the solution that contains G and the 4 vertices as we want them. Maybe here the value is 5. And if the value is not contained, we have a solution of 6 maybe, and then we just take the maximum of the 2. So in order to compute the solution where set S, we look, there's 2 options. It could be in the predecessor. Either the vertex is not, G is not contained, then this is the solution, or it is contained, and this is the solution, and we take the maximum of the 2 values. And at last, we have to think about how do we get the final answer of our dynamic programming routine. And here we simply look into the root. So the root bag R, then this set VR, all the vertices that are below the root will be exactly all the vertices of the graph. This is because of the first property of the tree decomposition that every vertex should be in some bag. And then computing the independent set in G is the same as computing the independent set in the subtree. And we know the bag is empty, so we only compute MR of the empty set. And what does this value contain? It contains the largest independent set that intersects the empty set in the empty set, which is just the largest independent set. So this is going to be exactly our solution. Which brings us again to our theorem that if you have a graph G and you're given a tree decomposition, then you compute the size of a maximum independent set in time 2 to the W plus some polynomial term plus times some polynomial term times linear runtime in N. Any questions about this theorem or what we just covered so far? If not, then I would like to note that so far we only computed the size of the largest independent set, but if you do a little bit extra bookkeeping by keeping representatives, you also can compute the independent set itself. And additionally, we had this constraint right now that you were giving the tree decomposition along with the graph. Can we ignore that perhaps? So maybe can we compute the tree decomposition? Unfortunately, it is quite hard to compute the tree decomposition of a graph, to compute the optimal one, but we don't really need an optimal one. It is okay if the tree decomposition is a little bit larger than the optimal one. Let's say it's worse by a factor of 2, and then there's a very nice recent result. So it is not a recent result that you can approximate the tree decomposition, but this paper from last year shows that you can actually do it with an approximation ratio of 2. So what does it state? There exists an algorithm that gets an n-vertex graph at an integer w and runs in time 2 to the O of w times n, and it computes either a tree decomposition of width as most 2 times w plus 1, or it concludes that the tree width is larger than w. So if the tree width is very large, you get a no, but if it's small, you get something that is most a factor 2 of. And you could use this now and do some kind of iterative search. You first ask, run this algorithm with w equal to 1. And then it maybe says, yeah, it's larger than 1. You run it with w equal to 2. And it may say, okay, it's still larger than 2. But then at some point, you will get something that is at most a factor 2 off from the optimal solution. And yeah.
Is this a case where like positive answer and a negative answer take vastly different times? It takes longer to actually compute the decomposition than to conclude that the tree width exceeds w?
No, in this case, the algorithm always runs in time 2 to the w times n, but you always get in this time either a yes answer or a no answer. Just that the yes and no isn't like a complete bipartition of the solution space. Either say it's lower than some threshold or higher than some other threshold, but yeah, it's somewhere in between then if you. But yeah, you can try out all the values up to the point where if you plug in w to be the tree width plus 1, then it will not tell you that the tree width is it cannot tell you that the tree width is larger than the tree width plus 1. So we'll get the actual solution, which is at most twice the tree width plus minus 1 or some other constant. So you do this all the way until you get something that is good enough. And the running time of this, of course, highly depends on the tree width. It depends on the tree width, how long you have to look until you find the decomposition, and also the running time itself depends on the tree width. And yeah, the running time that you get will be 2 to some linear factor in the tree width of n. And now you don't need the extra assumption that you are given the tree width decomposition. You just compute it using this routine, and then you do the dynamic programming, and then you get the size of the maximum independent set. So in summary, so far, we saw that tree width is a very nice graph parameter. It's perhaps one of the most widely studied graph parameters there are. And you can do some nice algorithm with it. Particularly, you can solve independent set in time some function of the tree width times n. So if you assume that your tree width is bounded by some constant, then some function of a constant will again be a constant, and you get a linear running time in the size of the graph. Yeah, and the way you go is using dynamic programming. And this does not only work for tree width, it also works for many other problems. Perhaps we will cover some of those in the exercise soon. But it would be kind of tedious to do it all yourself. So that's where the meter theorem comes in. And in summary, you could say that tree width is like a nice algorithmic detectable graph class. But just like for the sake of completeness, not everything is tractable if you parameterize it by tree width, or if you assume the tree width is low. For example, if you are given a graph and you're given some points like S1, T1, S2, T2, and you should find some disjoint path between this. This problem is already hard for graphs of tree width 2. So there's quite a bunch of problems where even unbounded tree width, they're hard because they're just so hard. But for many interesting problems, it turns out that they're tractable. So, for example, 3 coloring, I guess you should know. You want to color the graph with 3 colors, such that no vertices of the same color are adjacent. Independent set, we covered it already. clique can be covered by exactly the same algorithm, more or less. Dominating set, feedback vertex set, Hamilton path. We're going to talk about that in due time. And the way you would solve this kind of problems is by a similar dynamic programming algorithm. You start with the leaves and you push information up. And it would be kind of tedious to do it always all the time again, because it's very ugly to write this down, actually, if you want to be precise. So that's where we're going to have this nice meta theorem. And so the meta theorem, it's about logic and evaluation of logical sentences. So we're going to need some background in logic first. So I'm not assuming too much background in you guys, so let's talk about the very basics. So graph theorists and logicians, they have a bit of a different language. So I'm personally more of a graph person than a logic person. So for me, the notion of a graph, for example, is more common than to talk about structures. But for logicians, I guess it's the other way around. And here's like a quick dictionary how you could map these things one-to-one. So if we say graph, logicians say structure. If a graph theorist says subgraph or induced subgraph in this case, the equivalent term would be a substructure. A subgraph in terms of logic would be a weak substructure. And if we, as graph people, would talk about the vertices of the graph, then in terms of logic, this would be the universe of the structure. Sometimes we also put the edges into the universe of the structure. And if you pick a single vertex, this would be an element of the structure. And if in the graph, we usually talk about edges of the graph, but in logic, this could be an arbitrary relation. So an edge would be a binary relation between two elements. And if the edge is there, then the tuple is inside the binary relation. And you can also have colors of the graph, which would then be unary relations. And if you don't want to embarrass yourself in front of logicians, then it may make sense to learn all this vocabulary. But on the other plus side, you benefit from all these nice results that logicians prove and that we will, some of them, discover and use in the following lecture. So after this quick overview, let's try to be a little bit more precise of what logicians consider a graph. So they talk about structures, and structures, they have a signature, and a signature consists of relational symbols with given arities. What does that really mean? So here's an example of a structure. Let's say we want to create a structure that encodes undirected graphs. So here we're going to have a signature tau that contains a bunch of symbols. This will be a binary relation symbol, which will stand for the adjacency. And for every color of the graph, we will have a unary relation symbol. C1 for the first color, C2 for the second color. Sometimes we also just write green, blue, yellow, and so forth. And we say the universe of the structure will be the vertices of the graph. And this tilde, I use it to denote the binary adjacency relation between two vertices. So it will be a symmetric relation because the graph is undirected. And C1 will be the unary relation, which expresses that a vertex is colored with color I. And sometimes, if you don't want to talk about directed simple graphs, you can also have more complicated structures. For example, you can have like an arrow if you want to talk about directed graphs, or you can have like two sets UV as predicates if you want to talk only about bipartite graphs, and the list goes on. Whatever is convenient, you can use it, but there's certain things that are used more frequently. And yeah, I guess the most common way to express a graph is using a single binary relation and then colors. And to make things clear, here's an example of a graph encoded as a structure. So here we have this triangle graph, and it contains the vertices ABC. So we say the universe of the graph will be the vertex set V, or in other words, will be the set ABC. On the other hand, we have edges between A, B, AC, and BC. So we say that tilde is the binary relation that contains all the edge tuples. So it contains AB, but it also contains BA, because we don't distinguish between the direction of the edge. And similarly, it contains these tuples for all the edges of the graph. And at last, vertex A is colored red. So we have this predicate CI for the red vertices, which is only the A vertex, and C2 will be the set of blue vertices, which is only the vertex C. Is this clear so far? Great. And what comes next? MSO logic. So now that we have structures, we can talk about sentences that we evaluate on these structures. And for Treewidth, we're going to talk about MSO logic. And here, MSO logic contains element variables, which are lowercase letters usually, and set variables, which are usually uppercase letters. And you have a bunch of relations in the graph. So you have the equality relation. So you can write y is equal to x. And you can have a membership relation, which would be x is contained in some set x. But additionally, you have also the relations which are mentioned in the signature. And if we talk about graphs, then there's, for example, this tilde relation, and then you can write x is adjacent to y. But in principle, it could be any kind of relation that that you allow, that you want to have formulas upon. Question or just add switching?
Is this restricted to binary relations at most?
We're going to only talk about binary relation, but you can define monadic second order logic, I guess, over different structures as well. Then it could be like a hypergraph potentially. Okay. Then if the tau contains some ternary relation, then you can also define the logic on top of that, where you allow all those relations in tau.
But then the connection to just normal graph kind of breaks down.
Yeah, then you would kind of describe hypergraphs, for example. But yeah, if you talk about graphs, it will always be binary relations. And for the rest of the lecture, you can assume all the relations to be binary. Okay, and yeah, you have these extension universal quantifiers that can range over vertices and sets. And you have the usual Boolean combinations. And yeah, so I defined this for an arbitrary signature, but we're mostly going to use colored undirected graphs where the signature is exactly this binary relation for the adjacency and some extra relations for the colors of the graph. And in this context, we call the logic MSO1. So MSO1 logic will be exactly MSO logic where tau is fixed to this relation, one edge relation and some colors. Yeah.
Curiosity, is there a reason why we're taking a deal out of these colors? Is that crucial to
the question is why talk about colors? Because you can express some nicer properties with the graph. You can, for example, say that you want to look for a dominating set where all the vertices are blue. So it's mostly for convenience. You don't really need the colors. You can always encode the colors by adding some extra pendant vertices. And then say you want to look for a dominating set where all vertices have 5 loops attached or whatever. But it's just nicer to have these colors and you get them for free. And it's often quite useful to have them. And yeah, technically, usually you would write the relation in prefix notation, where you have first a relational symbol and then in parentheses perhaps the thing that you express an adjacency over or relation over. But I think it's just nicer in this context to write them using prefix notation. And then you may add some parentheses if things get confusing. Yeah. Any questions about notations so far? Great. Then here comes the first puzzle. What does this formula express? Just to make sure that we all get the semantics of MSO logic as well.
If G meant to be free,
Okay, this should be actually a G. Sorry,
at the end of the
this true. So here you're given a graph, and you have some red and some green vertices, and you say that it shouldn't be the case that you can pick a vertex here, and a vertex here, and a vertex here, such that there's a path from here to here to here. So it just expresses that the set of red and green vertices are separated with distance at least 2 in the graph.
Because we don't exclude the case that they are not allowed to be connected directly to the actions.
Yes, exactly. So it could still be the case that there's an edge that directly goes there. Yeah. So this is not excluded by the formula. And this is the case that I always forget if I write these formulas that, yeah, there's always a bunch of exceptions. But yeah, it seems like we get what it does. Here's another formula. Now this formula has a free variable. What does it say? Yeah.
the vertex cover.
X should be a vertex cover, you say? Anybody disagrees?
No.
So let's break it down piece by piece. So all vertices, they should be either contained in X, or there should be a vertex inside X that is adjacent to them. So here we have the set X. All vertices are either contained or they have an edge into the set. And this is what we call a dominating set. So yeah, I never formally defined this, but a dominating set is a set of vertices which covers the graph in the sense that all vertices should be either inside the set or have a neighbor in the set. And this is what the formula expresses. And next, we could talk about some technical observations about the logic, which can come in handy if you do some structural inductions on the formula, because the logic is a little bit redundant. You don't, for example, need disjunctions. If you want to say phi is true or psi is true, you can say it is not the case that neither phi nor psi nor phi is true. So in this example, this breaks down if and only if both of them are false, and this one also breaks down if and only if both of them are false, because if both of them are false, then this is true, the conjunction is true, and the negation would be false again. So this is just basic De Morgan applied to get rid of the conjunction. Similarly, you can get rid of universal quantifiers. Instead of saying for all x phi holds, you can say there is no x for which phi does not hold. And another convenient thing sometimes is that you have can convert the formula in Prefix notation, Prefix normal form, which roughly means that all quantifiers can be pushed to the front. So your formulas can be of the form exists x for all y, blah, 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 a bunch of quantifiers. And then you have a formula phi, which contains no quantifiers at all. So you can push the quantifiers to the front. That's sometimes convenient. And the way you would show it is by seeing that you can push a single quantifier to the front. So if you ask, does phi hold, and is there x such that psi holds, you can push the phi here into the formula. Because the phi does not depend on x, so it does not matter whether you quantify about x first or afterwards. You only need to worry perhaps about renaming variables. So it could be that here is another exists x outside, and phi makes statements about this x, but here, psi makes statements about a different x. And so these variables can be overwritten. It's always the narrowest quantifier that defines which x we're talking about. So then maybe you have to rename it to x prime everywhere, and then it should work out to do this transformation. Okay, that's just some tricks. And now one more definition. We say that phi is a sentence if it contains no free variables. And then we write this G and then this strange symbol phi to indicate that phi holds on G. And we read it as G is a model of phi. And the thing that we kind of did intuitively already is to express problems using logic. And we say that a property or a problem is expressible in a certain logic if there exists a sentence phi of that logic, such that for every graph holds phi is true if and only if G is a yes instance of that problem. So for problems, you will talk about yes instances, or if you talk about properties, you say phi holds if and only if G has this property. So is the following property expressible in MSO logic? What do we have to do? We have to write a formula which is true if and only if G has at least two vertices. So super easy. So it's x, this is y, and x should not be equal to y. Okay, now things get a little bit more tricky. Can you express the property that G is connected in MSO1 logic? Somebody's nodding. Let's give the others a moment to think about this as well. It's a bit counterintuitive how you would express it. Do you have an idea?
Yeah, I remember.
But
Sure.
we can say there are two so we gave it, but there are two non-empty sets which have no connection between them in the main gate. So when it would not connect, there would be two disjoint sets which are not connected to each other.
Okay, you say that there shouldn't be two sets which are disjoint and not connected. If the graph looks like this, it is connected, and we have this set and this set.
Yeah, but they have to be, and then they have to include every purpose.
That is exactly the solution. You say a graph is connected if and only if every partition of the graph in two halves is such that there goes at least one edge from the first partition to the second partition, from the first part to the second part. So in other words, the graph is disconnected if you can partition the vertices in two sets such that no edges goes between the two parts. So how do we, so that's a very nice property. How do we define it in MSO? I guess the first thing we need is there exists a set X and there exists a set Y. What properties should they have? Yeah.
For all vertices, it has all that they are either in X or in Y.
Yes, so now we enforce that X and Y are a partition. Yeah.
We have to enforce that they're disjoint, so that for all sets, not both and always not both. But now it has that they X and Y overlap.
It's not,
Wouldn't that express that it's not connected? If one express that it's connected, should they that there is an edge between the two sets?
Okay, yeah.
So now another, yeah,
So there exists no Z in X, no, so no node in X, and there's no node in Y such that they have a
I think that would again express non-connectivity. Or I would say there exists an X element X, and there exists a Y element Y, such that X is adjacent to Y. So, but now, what about, like we have these two two subparts, how do we logically connect them? First part expresses that it's a partition, and the second part expresses that there's an edge between them. I think we need an implication. So, for
I think we need the old quantifiers for the big X and Y, because we want to show it for every partition.
yes, so for all partitions, if this holds, then the thing below holds. So for all sets, if they form a partition into parts, then there should be an edge going from one set to the other set.
You need to switch the quantifiers, I think.
Yeah.
Oh, sorry, yes. I did not see there was an extension. For all X, for all Y. Or perhaps a bit cleaner is like this. For X, for all Y. If it is the case that X and Y form a partition, then there should be some vertices inside both sets that are connected. So yeah, here we have this extra operation, which is an implication, if this, then that. We never really formally defined it, that it's part of the logic, but you can have just phi implies psi. It's the same as not phi or psi. Okay, any questions about this so far? If not, then here is probably the last challenge for the day. Can we also express that 3 has a proper 3 coloring using MSO? Yeah.
We make a partition to two parts, and be sure that there is no edge between these partitions. So similar to the problem before.
Yes, that sounds good. We do another partition for all R, for all G, for all B. So now we have 3 sets that we quantify over, and you said if they form a partition, then there shouldn't be.
Now we need the extension because we asked if.
Sorry. Of course. Yes, there exists a partition RGB with a property. Maybe just write it casually. RGB is. RGB forms a partition. You can express it similarly to the way we did before. And additionally, what do we need?
Each vertex has exactly one color. This partition is in at least the way they expressed it in the previous.
Yeah, right now vertices could have 2 colors. Mhm.
It's not because we can just pick an arbitrary color.
Yeah, so if we do a coloring in a way that a vertex can have 2 colors, we're just doing more work that we actually need to do, because you can just like take it out of the set. But yeah, if it wouldn't hurt, and it would probably be easier to understand if we additionally enforce that every vertex is in exactly 1 color. Yeah.
in each partition, none of the vertices should be connected.
Each part
So
should be good.
none of your vertices in R should have an edge between each of them. And so forth.
So we could say,
They don't, it doesn't exist R1, R2
mhm,
without, so that there's an edge between.
like this.
If the other is strong.
It's not the case that there's
The other is strong, so,
two,
because now that's always true, because I can,
If the same vertex.
because I can take the same vertex here. That's version.
Why is that necessary? Because if you say that there doesn't exist like two verses, even if it's the same one, then this would kind of mean that it has a self edge.
It just means it has a loop, yeah.
Yeah, which
We only need that if there are loops.
No,
There's a
we don't.
negation and then,
okay, yeah.
you don't need that.
and probably not necessary, I think.
For the negation.
So I think the whole formula looks kind of like this, if we take your suggestion also into account. So let's break it down part by part. So first part says all vertices should be either contained in R or in G or in B. Just means the stuff we talked about earlier. And now the second part, which actually enforces that every vertex has except one color, which is not strictly necessary, but here we say for all vertices X, it is not the case that X has both color red and green, and it's not the case that it both has color green and blue, and not the case that it both has color red and blue. So just so far we have that every vertex has exactly one color. And next, we're going to iterate over all tuples X and Y. And we say if they have the same color, so in the sense if they are either both red or both green or both blue, then they shouldn't be adjacent. Okay, so this formula now expresses three coloring. And I suppose next lecture we're gonna then talk about the model checking problem. So here the problem is you're given a graph and an MSO of sentence phi, and you want to decide whether the formula phi holds or does not hold. And if you can solve this problem, then you can solve all problems that are expressible in this logic MSO1. So if you can evaluate the MSO formula for three coloring, for example, then you can solve three coloring. And so the model checking problem is quite hard because coloring as a special case is hard. But on Treewidth, we're going to actually be able to evaluate these kind of formulas. But that's something for the next lecture. So any questions until now? Then I would like to thank you for participating nicely, and okay, and we see each other not next Tuesday, but in the week after on Friday for the first exercise. So thanks. Bye.